chapter information is just like information. So like just telling you information. But then a lot of the chapters is like asking questions, posing questions, and then you give me what you think might be answers. They might be right or they might be wrong. There is like, you know, there are right and wrong answers, but when I ask you a question, there's no right or wrong. If you're wrong, then I'm just like, that's close. But sometimes we have something that's a little better. Just ask for some feedback in it. So here's the first part. So in this first part, we're going to do some what I call old school definitions. So sometimes this may come out of your mouth and you forgot that you knew this because maybe you had it way, way, way back when, or maybe it's just something that was like shoved down your throat for like 5th, 6th, and 7th grade, and that's why you remember it. So old school definitions. So chemistry. As a definition, chemistry is the study of. So this is on your PowerPoints. Did you get the handout with the PowerPoint handout? Yep. Yep. Very second slide. Okay. So this would be called, so chemistry, biology, physics, these are very organized systemic studies, go through sort of like one step, next step, very much the same. It is the study of what? When you think of chemistry, it's the study, the study of the earth, the study of all of the stuff that makes up the universe. So that is elements, compounds, all of those fall into this. This is the study of matter. It's the study of matter and all the changes it undergoes. So this includes everything from like when you take ice cubes out and they melt, so they go from solid to being liquid. Also included like when you light a fire, so you'd start the charcoal briquettes and at the end of the night, they're nothing but just ash. Okay, so matter changes forms, so that is all part of chemistry. Matter, by definition, has two things. It's anything that has mass and takes up space. Okay, did you remember that? Or is that something? So it has mass. And by mass, think like weight. Okay, the amount of stuff that makes it up. And it takes up space. I don't like red. Takes up space. By space, think volume. Okay? So it takes up some amount of space. So I always think of matter as a noun. So matter are things that are solids, liquids, and gases around you. Okay? So you think of solids like the desk. Okay? You think of liquids like your soda. Think of gases like the air in the room. All great examples of matter. Now, these are different because of how the particles that make them up are arranged. So which of these three have particles that are as close as possible? Solids. So if you were going to draw 10 little dots with solids, put them as close as you can. Right? They're in a very regular, rigid arrangement, like touching one another, packed in very tight. Because of that, solids have a definite shape, right? So the desk doesn't just change shape, okay? They also have a very definite volume. They have a definite shape and volume. And I do try to write, but I am left-handed. That is my excuse. See, like that doesn't even look normal. Volume. Now, how would you say liquids? If you were going to put the dots for liquids, how would you put them? A little more apart, right? So instead of being like this, there's a little bit of space so that they can flow. Okay? So put these 10 dots. Put your 10 dots again. But now, put a little bit of space around them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so with that, they can flow. So they have the ability to slide past one another because there is this space. Solids can't do that. So shape. Do liquids maintain their shape? No. They take up the shape of their container, right? So liquids have a variable shape. But what about their volume? So if you have that 20-ounce Pepsi, if you pour it into a glass, is it still 20 ounces? Yeah. If you spill it on the floor, it's still a mess to clean up, but it's still 20 ounces, right? So the amount in that bottle is its volume, and it takes up the same irregardless of where it is. You could put it in a wide bowl or a really tall cylinder. It's still going to be 20 ounces, same, so it has a definite volume. Now, what would you say about gases? If you were going to draw 10 dots, how would you draw 10 dots that are gases? Very spaced out. Okay. In fact, the gases in this room, the particles, the odds of these particles actually hitting each other is like more than 1,000,000 to 1. They're that spread apart. Gases like to spread out as much as possible. So if you're going to put your 10 dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Spread them way out. So what's that going to do to their shape? Is it constant or changeable? Changeable. So it's a variable shape. What about volume? Has anybody ever had to use an oxygen tank? Okay. So an oxygen tank, you take a sample of oxygen and they press it into a very small cylinder so it doesn't take up so much room. And then when you release the tank, the air or oxygen begins to flow out so that you can use it as a nasal cannula. You can put it for a mask. So you can actually take gases and squeeze them into smaller spaces. But if you don't do that, they will fill whatever their space is. So they have both a variable shape and a variable volume. Which one has the most energy? Which one of these particles, if we're looking at each of those dots, which set of dots has the most energy? Is moving the most? Gases. Highest energy? That's why they have to have so much room, because they vibrate. Okay? They're moving constantly. So that means solids are going to have your lowest energy. So that now leads us to the next question. Okay, lowest energy. What's energy? Energy is not matter. Okay, so energy is not matter. It is not a noun. What is the definition of energy? It's the ability to do work. See, you did remember it. Where did that come from? That's the part that always makes me laugh, because people are like, I didn't even know I knew that. Like, it just like bloop, comes out of my mouth from some deep recess in my brain that I learned. So energy is the ability to do work. So work, you can see the effects of work, but you can't see work. So in here, we can have kinetic energy, we can have potential energy. So where is work doing something in this room? Okay, kinetic is active, doing work. This is active work or active energy that is doing something. So where can you think in this room, where is there energy that's doing work? The what? Okay, so a printer, all right. So the printer, that would be, to run the printer, what do you have to do? You have to turn it on, so that's electrical. Right? So if it's not on, that's potential, right? Because being potential means it's like stored. It's inactive at that time. So if it's inactive or stored energy, electrical, good example. Electrical energy is the flow of particles along a wire. And I always think of these lights. So the lights in the back of the room, those are kinetic energy forms, because when you flip the light switch, it actually closes a circuit. So in order for a light bulb to light, electricity has to flow through a filament and the filament glows. If you flip off the switch, it actually breaks the circle, it breaks the circuit, and that's why it shuts off. So you would say these lights, these have potential energy. These could light, I just have to flip the switch. Okay, so these right now are not glowing, but the ones back at the back are. Okay, so lights. anything that's plugged in, our LCD projector. Now, what about what you're sitting there doing? What kind of energy is that? It is kinetic because what are you doing? You're writing, movement, okay? Muscle contraction is mechanical. Mechanical energy is the energy of movement. Whether you're walking, writing, any kind of movement. This could even be like the wind blowing, like in that storm last night. That was pretty hefty, right? So you can't see the wind, but you can see the trees like, you know, and then this way, and then this way. They were like going one direction and the other direction. I was like, I'm not sure these trees are going to be able to make it tonight, but ours did. But that's kinetic, okay? It's kinetic because the wind is blowing. It's kinetic mechanical because you can actually then see its effects. So we are also going to talk in class a lot more about chemical energy. So chemical energy is the energy that's contained in molecules. This is the energy in chemical bonds. And a good example of this is food or your soda, okay? So in your soda, what is one of the nutrients that's in your soda? If it's regular soda, not diet. It has a lot of sugar. Yeah. Caffeine is just a stimulant. It's not actually broken down for energy. Remember, carbohydrates, proteins, and fats, those are your three nutrients. So there's a lot of carbohydrates, simple carbohydrates, which are sugars that are found there. So what your body does, you absorb these nutrients and your body can break them down by breaking the chemical bonds that hold the nutrient together, and that releases the energy. And then you can use that energy to power your muscles, to run your brain cells, okay, to do all of the other work that the cell has to do. So once you drink this, now once it gets digested and absorbed, now it is actually kinetic energy. But while it's still in the bottle, what is it? That's potential, right? So food on the shelf or uneaten food, that's a good example of potential energy because it doesn't become kinetic energy until you ingest it. Okay, and then your body cells can actually use it. So just a good way of trying to think about like active energy versus stored or potential energy. We are going to talk about nuclear energy as well. This is chapter 2. So nuclear energy is the energy that's contained within atoms. Some atoms have the ability to release energy as they change form. So we'll talk about radioactive substances, about like radiation treatment in cancer treatment, about nuclear power plants. So we'll talk about how this type of nuclear energy is used in your everyday life and people that you know probably have been affected by it, and then also how it can be sort of beneficial. So lots of different forms of energy that exist, but above and beyond, all energy comes from the what? All energy on Earth ultimately comes from the sun. See, there was another thing that just came out of your head. Okay, so solar energy, which is sunlight. And that is ultimately the power of, that's where all of this energy comes from. It gets transferred into chemical energy. It can then get transferred into nuclear energy. So it can be used and transformed into other types of energy, but that really is that origin for the Earth. So we've talked about matter. So we said matter, this is anything that has mass, so characteristics. It has mass and it has volume. So it has some substance to it that has a heaviness, that has mass, weight, and it takes up space. So thinking about solids, liquids, and gases, they also classify matter according to if it can be split into smaller parts or separated into individual parts and pieces, or if it's uniform throughout. So there is a second classification of matter where you say matter can be a mixture or matter can exist as a pure substance. So if matter is a mixture, that's like your soda, right? What do you know is in your soda? So one person said in your soda is caffeine. Also in the soda is sugar. Also in the soda is flavorings, right? Like the cola flavorings. Also colors to make it brown in color.
Acid.
It's got acid. It's got carbonic acid, which is what they pump carbon dioxide into it to give it the bubbles. So the most of it, though, is water. So there we've just gone through just in general, not even counting the preservatives and all the other stuff that they put in there. Okay. Just in general, we've got 6. But are those chemically combined or just physically mixed together? They're actually just physical. Okay. They're just physically mixed together. So they just put them together and like compress them into that bottle and then seal it. And there you go. Now you got your soda. So that is a mixture. So mixtures are physically combined. They could be 2 things, 4 things. They could be 200 things. Okay. It's more than one thing that is physically combined. And so could I separate that? Yeah. So if you physically put things together, you could physically separate them out. Like I could boil the water away and that would leave the residue stuff behind. So if you can physically separate, it's a mixture. So like whole eggs, is that a mixture? Yes or no?
It can be separated.
It could be separated, right? We could separate the yolks and the whites, right? So think like physically, can I actually split them apart? Okay. What about like black coffee? Do you think it's a mixture? It's a mixture, right? Because you put water through coffee grounds and you get this brown liquid that comes out. So you dissolve the stuff that's in those brown coffee grounds. So water came through plus all this other stuff that's in the coffee grounds. That's a mixture. But a pure substance, I can't separate it. Okay, so pure substance, so for example, aluminum foil. Okay, so if you take a piece of aluminum foil, tear it in half, are they both aluminum? Tear it in half, are those both aluminum? I keep tearing and tearing to teeny tiny little pieces. Those are all aluminum. I can't separate it into 2 different things. That's what a pure substance is. So a pure substance is composed of only one kind of substance. And a pure substance then cannot be physically separated. So a pure substance is only one kind of substance that makes them up. Whereas mixtures is more than one thing that have been physically combined. So mixtures, you really describe mixtures based on how they look. So you say a mixture is either heterogeneous or homogeneous. Homogeneous is another way of saying it. Homo means what? The same. So something that is homogeneous, if you have a homogeneous mixture, there is more than one thing physically combined, but when you look at it, it looks uniform. So if it's homogeneous, this is going to look uniform. So going back, my example of black coffee. When you pour coffee in the cup without anything else, does it look all the same at the top and at the bottom? Yeah. So you would say that's a homogeneous mixture, but I know it's got water, it's got caffeine, it's got the brown pigments out of the coffee grounds. So I know it's a mixture, but it looks the same. That's homogeneous. So can you give me an example of one that's heterogeneous? What does hetero mean? Different, right? So, So flour.
What about oil and water?
Oil and water is probably a better example. So flour, if we had pure flour and it was nothing but just starch, that would actually be a pure substance. Okay. But most of the time they put stuff in flour to keep it from like clumping together. So that's why I'm like, it's got some other little bits in there. So it is a mixture, And it would be more on the homogeneous, because if you look at it, it just looks like white particles. But oil and vinegar is a good example, because when you have oil and vinegar, what do? Separate, right? Oil and water is going to separate out. Italian dressing separates out. So you get these two layers, and you can see it. Okay, so you can see that there's definitely two different things in here. Okay, so heterogeneous is going to look different. Heterogeneous, I'm going to have layers. Right? Layers, pieces, parts, little bits. Like I even think like ranch dressing. Like you get ranch dressing, it's got like little things in it. Like it's more white, but it's not solid white. It's got, and so it's like mayonnaise, I would say, is a homogeneous mixture. Okay? Because mayonnaise is actually egg yolks and vinegar and water all mixed together. Okay, but ranch dressing, you see like little green bits, little black specks in it and stuff. So that's going to be heterogeneous. So because I can see parts. So oil and water, good example of heterogeneous. Salad dressings, like ranch dressing, Italian dressing, good examples of heterogeneous. But pure substances usually tend to look the same. So sometimes people are like, well, pure substances always look homogeneous. Like the aluminum foil, like if I split it, does it still look the same? Yeah, it still has this like shiny silvery metal. Even if I cut it into little tiny pieces, it's just a bunch of little shiny silvery metal pieces. So pure substances tend to look homogeneous. Pure substances can either be an element or a compound. Elements, you can identify a pure substance. If it's an element, it's going to be there on the periodic table of the elements. Okay, this actually has the entire list of all the possible elements. So CAl, Al is aluminum. So if it's an element, it's on the periodic table. Al, aluminum. So some of these might be familiar. So looking at the periodic table, and I gave you a laminated copy. You can always pick up that laminated copy of the periodic table when you come in. Please don't take it home with you though. Okay, make sure that you put it back on the pile on your way out. We laminate it because I use them. Like I will always give them out to you. You can keep it until on your way out. Always just put it back on the pile. In fact, I did give you on the handout that has like the unit conversions, the very last page. The very last page is this. Okay, so you got a copy. In fact, make sure you bring this next time because you can write stuff on this so that you will have it like to remind yourself, okay, I got to know this one, I got to know that one. Thank you so much. Okay, so elements on the periodic table. So like I said, like Al, that's aluminum.
So we can go ahead and write aluminum on our periodic table.
Mm-hmm. And I'll actually, 4 or 5 slides ahead is going to be a list of the elements, names, and symbols that you need to know. Okay, so you can wait. That'll end up being next time that we're going to talk about that. But we'll go over which ones you need to know specifically. You do not have to memorize all 118 elements on the periodic table. Okay, promise. But some of them might be familiar now. C, capital C, it's number 6 on the periodic table. What is that? Carbon. Mm-hmm. Capital C is carbon. Capital H. Hydrogen. Capital O, oxygen. And notice the first symbol, the first letter is always capitalized. And then capital N, nitrogen. So I tell you these 4, C, H, O, and N, these make up 96% of the atoms in your body. Okay? Carbon, hydrogen, oxygen, and nitrogen. These are the primary atoms that you find in carbohydrates, in proteins, lipids, and nucleic acids. So 96% of the body is made of those 4 atoms. They call those the main atoms or the major elements. So in living things, carbon, hydrogen, oxygen, and nitrogen. Until we'll talk about it in another slide coming up anyways. But that's like, if all these would be called elements though. If I just have a sample of carbon, it's on the periodic table, it's an element. So I know it's a pure substance and it's an element because it's on the periodic table all by itself. We can have pure substances that are actually combinations of more than one element that are chemically combined. So an example of this is a compound. So this is two or more elements. These are not physically combined. So it's not like I took carbon and oxygen and rubbed them together and mixed them. Instead, carbon and oxygen can be mixed together in a definite ratio. These are chemically combined, which makes them different than mixtures. And they combine in a fixed ratio. So most people know this. What is this? Two or more elements that are chemically combined in a fixed ratio. Okay? This is carbon dioxide. So another one, CO2. Okay? So my example, CO2, it just looks really terrible. CO2 is carbon dioxide. So the formula CO2 tells you how many carbon and how many oxygen in one molecule. Tells you that there's one carbon and two oxygens. Yep, that's a C.
Oh, is that RATIO?
Yes, ratio. Like, it just means that they're always the same. So here's another one. Water, right? So water is always H2O. It's not H3O or H2O2. Actually, H2O2 is hydrogen peroxide. And you don't want to drink that, okay? Because that will definitely make you vomit. All right? But you drink water, you're supposed to get like 2 liters of water a day. They only differ by 1 oxygen. So they're that similar, but they have very different characteristics because of their formula. So H2O means 2 hydrogens, 1 oxygen. If there's only one of an atom, they don't put a 1. So that's why like CO2, there's no 1 after the C, but that means you have 1 carbon. But then O2 tells you there's 2 oxygen. The number after the element tells you how many. So one of the things that we're going to use in lab tonight is C12H22O11. So C12H22O11, how many carbon? 12. How many hydrogen? 22. And oxygen? 11. That's table sugar. Okay, that's sucrose. It's just table sugar. So we're going to use some table sugar in lab tonight. But that's a lot of atoms. That means one particle has all of those. Yes, so we are finishing up 6:43 right now. Okay. It's 7. Yeah, so we got like a 15-minute break in between. Okay.
I'm online. Do you mind if I sit in on this sometimes, or I can't do it?
Oh, for the lab?
Yeah.
You could just switch to the lab if you wanted to.
They said it was closed. Yeah, because I'm trying to take the lab online. It's something I had to do. One or the other. Like you can't.
Nope. You can do one online and one not. But the lab's like is a $200 lab kit if you want to do the online lab. So you can talk to me after class about it. So this is what I want you to practice for next time. Okay? So for next time, what I want you to do is this first column, I want you to identify, is sodium chloride, is it a pure substance or is it a mixture? 10 karat gold. What does 10 karat mean? There's 10 karat gold, 14 karat gold. The highest gold is 18. What does it tell you?
It's real, baby.
Any higher than 18 and it's too soft, you can't make it into jewelry.
It's 24 karat.
It's so bendy though. 24 karat gold, you have to have it has to be a certain thickness because the gold is too soft. So what they do is they add other metals to it to make it harder. So 10, 14, 24 karat, 18 karat. I don't see a lot of 24 karat gold anymore. Like cost-wise, because it's what, like $1,200 an ounce or something like that. But this carat means the amount of gold compared to other metals. Okay? So this is a couple further forward.
I'm gonna email you.
Okay. The other one that I want you to add in for ammonia, NH3. That's what ammonia is. I will tell you that air is a combination of nitrogen and oxygen. And asphalt if you have been driving on 64 for the last 3 months, you have like encountered asphalt trucks, the little asphalt dinosaur chompers. Okay. It's like everything. Asphalt is made of tar, rocks, and sand, and old asphalt. So I'll just tell you that. All these other ones, you should be able to like think about what they are. So first column, identify, is it a pure substance? So is sodium chloride a pure substance or a mixture? So you're either going to put pure substance or you're going to put mixture here. Second column, if it's a pure substance, then stop. If it's a pure substance, then I want you to identify, is it a element or compound? Or if it's a mixture, is it homo or hetero? Does that make sense? Mixtures are going to be homogeneous or heterogeneous. So if it's a pure substance, then you're going to tell me, is it an element or a compound? If it's a mixture, then you're going to tell me, is it a homogeneous mixture or is it a heterogeneous mixture on this second line? So like sodium chloride, is it a pure substance or a mixture? Sodium chloride. It's a pure substance. If you have pure salt, there's nothing else in it, it is a pure substance. So if it's a pure substance, so remember, pure substance is either going to be on the periodic table or you're going to have a formula. Okay? So notice like NaCl. If you see a formula and there's only one, or if you see it's something that's listed on the periodic table, then it's a pure substance. So is this a compound or an element?
No, that's a compound.
It's a compound. Why?
It's not up here.
Okay, it's both of them. See how it has Na and Cl. So compounds are 2 or more elements in the formula, right? So this is going to be a compound. Whereas if I have like carbon, so if I said carbon, you'd say that's a pure substance. It's an element because it's listed all by itself on the periodic table. Okay, so pure substances are either going to be an element or you'll have a formula. Okay, so you'll have a formula like H2O, right? So then you know that that's the compound. Most of the other ones, they're always going to be mixtures. So you've got to think in your head, are these a bunch of things all mixed together? Okay, and then if they are, do they look uniform? They're homogeneous. Or do they look different? If they're different, they're heterogeneous. Okay, so for Sunday night, finish your pre-lecture chapter 1, and then also work on this. So there's a dynamic study module that talks about solids, liquids, and gases and the characteristics of them, which we talked about in class, and also talks about pure substances and mixtures, differences with homogeneous, heterogeneous. Okay, so we've just talked about it, so it shouldn't take you all that long to do these. It's everything we just talked about tonight. Okay, and then try to do this for class. We'll answer these ones directly in class on Monday night.
This one right here.
Yep, this one. Okay, so make sure that you bring all of your handouts with you on Monday night because we are going to talk about more of the things that I gave you that I haven't specifically talked about yet.
I'm sorry, Miss Carmichael.